Chapter 19, Nuclear Radiation, Part 1. These are the topics for Part 1, radioactive isotopes, types of radiation, nuclear reactions, nuclear stability, and radiation measurement. This is a cartoon I got out of a magazine many years ago. I think it illustrates the point that radiation's been around us forever. You can see here with the caveman, 50,000 BC, he's asking a fellow today, what's the radiation level like in AD? And he says, much the same as BC, mate. So in other words, we've had radiation around us forever. And we've kind of learned to live with it. Mostly you find radioactive elements not existing in large amounts in any one place, but more spread out over an area. So for the most part, we're always exposed to what we call background radiation. Let's take a look at this slide. Here we have some different radioactive isotopes to check out. We have magnesium-24, which is stable, and you notice we call it 24 because we have to say the mass number with it, and that's compared to magnesium-23 and magnesium-27, which are both radioactive. And so for the radioactive isotopes, we either have more or less neutrons than the stable one. We can see the same thing here with iodine-127. If you compare the mass numbers for the radioactive isotopes of iodine, we have a mass number greater and one smaller than 127. So there's something about the neutron to proton ratio in these elements that are making them radioactive or stable. Now for uranium, we don't have any stable isotopes. All the isotopes of uranium are radioactive, which means unstable. So an unstable nucleus is one where the number of protons to neutrons isn't right. Something wrong with it, and that nucleus starts to break down, releasing bits and parts of its own nucleus to change that neutron to proton ratio. Now we're going to see it in much more detail later on. Now here we have a periodic table that lists where the different elements are that are where all of their isotopes are radioactive. And so you notice that starting right here with polonium, all the isotopes of elements with atomic numbers higher than 83 are radioactive. So we're starting here. We have polonium, astatine, radium, and since all this group here, all of their isotopes are radioactive, and also down here. Now you notice also it says technetium and promethium are also radioactive, and they're located right here. We have PM. And we have TC, technetium. So for the most part, most elements are stable, and that they do have radioactive isotopes, but most of the isotopes that you find for these elements are stable. But just way down, the very heavy ones are the ones that are unstable. Here are the different types of radiation that we're going to be talking about today. So we can have alpha particles and beta particles. This is the Greek letter alpha, Greek letter beta. An alpha particle is a pretty big particle. In fact, it's the largest type of radiation. It consists of 2 protons and 2 neutrons. It has a mass number of 4, and it has no electrons, so it has a charge of +2. A beta particle, on the other hand, is actually an electron that comes from the nucleus. When a neutron decays, and it can decay, a neutron can become a proton plus an electron. So it would look like this. Here's my neutron, N. The neutron can become a proton plus an electron. Now the electron comes flying out of the nucleus with a lot of energy, and then it's called a beta particle. And what happens when this occurs? Well, the mass number pretty much stays the same because a neutron and a proton weigh about the same amount. But the atomic number goes up by 1. So that means we wind up getting a new element. Now we can also have what we call a positron, which is a positive electron. Now for both the beta particle and the positron, because they have no mass, we have 0 at the top, and the numbers on the bottom are really the charges. A gamma ray is also a very common type of radiation. Now a gamma ray, because it's a form of light, has no mass and no charge. That's Greek letter gamma. We can also have protons and neutrons coming from an atom. Now the protons, small p, can be represented by a hydrogen atom since hydrogen only has one proton in its nucleus. So this can represent a proton. Oh, we can have, small p in there with the 1 and the 1. Now N for neutron is always a small n. So you got to be careful here. Don't put in a capital N because that's nitrogen. So for the neutron, we have a mass of 1 and we have no charge. In this slide here, we can check out the risk that the different types of radiation can have on us. First of all, let's check out the alpha particle. Now, an alpha particle represents the greatest internal risk. In other words, if you were to ingest a radioactive substance that's releasing alpha particles, once it's inside you, those alpha particles cause all sorts of havoc. They smash into molecules, they create ions and radicals, and usually bad chemical reactions will happen and you wind up dying from it. The most poisonous substance in the world is really like plutonium, which can release alpha particles when it decays. A small amount of that in the drinking water would kill thousands and thousands of people. Now, they wouldn't put plutonium metal in. What they do is put a plutonium compound in. One thing about these radioactive atoms is that chemically they're the same as non-radioactive elements. You can combine them with other elements and make compounds, and then the compounds are radioactive. Because radiation comes from the nucleus, so it has really nothing to do with chemical reactions. So then the compound would be radioactive, and then it would act like, that compound as if it was not radioactive. It would be soluble in water, maybe. It could be an ion and still be radioactive. Again, because an ion has nothing to do with the nucleus. Well, anyway, alpha particles represent the greatest internal risk. Now, externally, alpha particles kind of can penetrate the skin. So if that radioactive substance is outside of you and it's releasing alpha particles, there's no danger. Beta particles, on the other hand, can penetrate the skin up to a few millimeters and cause, skin cancers. But they can be stopped by aluminum foil, as you can see here. Now, gamma rays and X-rays can penetrate the skin, and they can only be stopped by lead. They can cause all sorts of havoc. So if you're exposed to a radioactive substance that's releasing a lot of gamma radiation or X-rays, then you have a problem. When you go to the dentist or maybe you're in the hospital and you have to have an X-ray, they always put like lead shielding on you to protect vital organs, especially the sex organs, from being exposed to gamma rays and X-rays. Now, neutrons, which can be produced in nuclear reactions like fission, they can even penetrate lead, and they have to be stopped by concrete. So when an atom bomb is detonated, you get a shower of neutrons besides all the other effects. And so it's almost impossible to escape that unless you're really behind a lot of concrete. Now, Alexander Litvinenko was a former Russian spy who became a victim of Putin. Now, when the Russian government collapsed back around 1990, a lot of the people that worked for the government, including the KGB, they were just let go. And so Litvinenko went to England, and he was going to write a tell-all book about the KGB. And Putin didn't want him to do this. And so as the story goes, he was poisoned by somebody putting down a compound that contained polonium-210, an alpha emitter, on his salad. And when he ate part of that salad, he got sick and he died of radiation poisoning about a month later. A very painful way to go. It's like dying from AIDS. The radiation just causes all sorts of chemical reactions inside you, winds up wiping out your immune system, and you die very, very poorly. And there's nothing you can do. There's nothing you can take to stop this from happening. Okay, let's take a look at alpha emission in particular now. So here we have a radioactive nucleus, and these lines tell you that it's unstable. It's uranium-238, and it's going to decay by releasing an alpha particle. Here's our alpha particle up here. Here's our symbol for it. And then the uranium-238 becomes thorium-234. Now we're going to write an equation that shows this. And here's the equation now. You're going to be asked to usually figure out one of the missing particles in these equations. So here we have our uranium-238 nucleus. Here we have thorium-234, and here's our alpha particle. Now these are very easy to do because you notice we're starting with a total mass of 238. And on the right, if you add these numbers together, we have 238 again. And the same here, we're starting with 92 for the atomic number, and 90 and 2 is 92. So mostly what happens is one of these two is unknown, and you have to figure out what it is. So you get the numbers first, and then you look up the atomic number on the bottom. Not the mass number, but the atomic number. And then you get the symbol. So here's one for you to try. So polonium-212 decays by alpha emission. Write a balanced nuclear equation for the decay of polonium-212. Now if you want to give it a shot on your own, you can pause the video at this point and try it, and then come back and you can check out the solution. Okay, here's the solution. So this is going to be the symbol we're going to use for an alpha particle. We can use either one of these two. I'm probably going to use this one here. So I start with polonium. I have my polonium-212, then I have my arrow, and then I have my alpha particle, and I'm trying to figure out what X is. And so it's really pretty easy to do. I know that 212 on the left has to equal 212 on the right. 84 on the left has to equal 84 on the right. So what's missing then? 208 and 82. So I look up the 82 to get the symbol, and I see that's lead 208. Pretty easy and straightforward. Okay, next let's take a look at beta emission. So here we have carbon-14 that's unstable, and it's going to release a beta particle, and when it does that, it becomes a stable nucleus of nitrogen-14. So to write an equation, we start off with our carbon-14 symbol, and again, one of these would probably be missing, so you have to figure out what it is. It's possible to have this one the unknown as well. It doesn't really matter. As you look at the numbers, 14 on the left, these two must add up to 14. 6 on the left, these two must add up to 6. Now you notice that we have -1 here. So some people do these too quickly and they forget that it's a -1, and instead of putting down a 7 here, they put down a 5 because they think that's a positive one. So it's really 7 minus 1 equals 6. Pretty straightforward. Now nuclear transmutation is a little bit different than decay. In nuclear transmutation, we can actually take, and here's a couple of examples. Let me do one at a time here. Here we have a nitrogen-14 atom, and we're going to hit it with an alpha particle. And what happens is they combine together, and then they split apart into two other particles. We have oxygen-17, and we get a proton. You notice that the numbers, though, add up again. 14 and 4 is 18. 17 and 1 is 18. 7 and 2 is 9. 8 and 1 is 9. So one of these, of the 4, one might be missing, and you have to figure out what it is. Here we have aluminum-27, which is stable. And by hitting that with an alpha particle, we wind up making phosphorus-30, which is unstable. So this is how we can actually make a radioactive element from a non-radioactive one. Just like nitrogen-14 is stable, non-radioactive, we make oxygen-17 from it. Now here we are hitting the nitrogen-14 atom with a proton. If we can get that incorporated into the nucleus, it'll break down, and then we get carbon-11, which is radioactive, and we get an alpha particle produced. So these are examples of nuclear transmutation, which means you're making a new element from another element. Now to do that, we use I don't call it a machine, but it's more of a device called the cyclotron. And this is a picture of one of them here. My arrow. What you wind up doing is you have your target, and then you have your bullets. In this case, these would be the bullets, like alpha particles or protons, and you get them spinning faster and faster in these, and it's like almost like a racetrack. And then you hit them at the target, and hopefully you get what you're looking for. So by alternating the magnetic field, they can take these particles which have charges, and they can get them moving faster and faster and faster. So an alpha particle would be our biggest type of bullet. A proton is smaller. But all of these are positive charged now. Now this gives you another example like we had before. You notice again, here we have an alpha particle, And the numbers add up. 4 and 10 is 14, 13 and 1 is 14. Now, what about stability anyway? Well, let's check this table out. Now, this is a great little table to give us some idea about, can I predict if a nucleus might be stable or not? So what you notice is that even numbers of protons and neutrons seem to mean stability. There's something about even numbers of both that gives you the most stable isotopes, whereas odd numbers of both give you just a few stable isotopes. So even numbers then are better than odd numbers. Also, we find that if you have neutrons or protons with these numbers here, and these are called magic numbers, that seems to confer some stability on the nucleus as well. Now, nobody knows why. There are some possible ideas to this. Some people believe that a nucleus is really like overall an atom with the electron levels. Maybe there are levels within a nucleus where the levels more consist of alpha particles, different numbers of those, because alpha particles are all even numbers of protons and neutrons. And these numbers here, as I mentioned in the slide, these are the numbers that seem to confer stability on the noble gases. These are the number of electrons, and we see those same numbers for the number of protons. So again, these are magic numbers. So what makes a nucleus unstable? Again, no one really knows, but we do know that the number of protons and neutrons for some reason isn't right. And that nucleus decomposes, it spits out bits and pieces of itself that we call radiation. And when it does that, it changes its neutron to proton ratio. So for elements 1 through 20, it seems that the stable atoms are the ones that have a neutron to proton ratio of 1, regardless of whether they have even numbers or odd numbers of protons. So neutron proton ratio to 1. Here is our example with magnesium 24. 12 neutrons and 12 protons, that's 1. Nitrogen 14, it's also going to give us a ratio of 1. Now here you notice that both of these are odd, but the main thing is that the neutron-proton ratio is just 1. Now heavier elements seem to need more neutrons than protons, so the ratio is greater than 1. For instance, uranium-238, the ratio is 1.59 to 1. For lead-208, the ratio is 1.56 to 1. So lead-208 is more stable than uranium. In fact, lead-208 is not radioactive. So you see the neutron to proton ratio is a little bit smaller. It seems like you're trying to get to that 1.5 number. For polonium-212, 1.52, you notice that's more stable. We have what we call the band of stability, and that's what this chart shows here. So you notice for uranium-238, 1.59 is the neutron to proton ratio. For calcium-41, 1.05. So you can see down here for number of protons or atomic numbers, you see as long as they're around 1 through 20, the ratio should be like 1 to 1. But once you get larger than that, as the number of protons increases, so does the number of neutrons, even by a greater number. And we see our band going like that. So what happens if you have an element up here someplace off the band? Well, in order to get closer to the band of stability, it would have to change its neutron to proton ratio. So if it's too large, it has to increase the number of protons and decrease the number of neutrons. And when a beta particle is emitted, that's exactly what's happening. So you can kind of predict sometimes whether a radioactive nucleus will emit an alpha or a beta particle. Now what happens if it emits an alpha particle? Well, both the neutrons and the protons diminish by 2, and that will change the ratio a bit as well. It makes a smaller nucleus. And a smaller nucleus is usually more stable than a larger one. What about if we're down here? Well, if we're down here where the neutron to proton ratio is too small, then we have to go the opposite way. We have to change protons to neutrons. So that can happen by positron decay or by electron capture. Now in electron capture, electron gets close to the nucleus and it's captured by a proton. And when that happens, the proton becomes a neutron, and that shifts the ratio a bit, makes it a bit larger. Now this will give you an idea here. This is the decay series for uranium. So we start up at the top. Uranium-238 And this is its half-life. Now in part 2 we're going to go through half-life very carefully. So just know that a half-life tells you how long it takes for half of a sample to decay. The longer the half-life, the slower these atoms decay. So you can see for uranium-238, the half-life is 4.5 billion years. That's an awful long time. But whereas what happens here, the uranium-238 atom releases an alpha particle and becomes thorium-234 with a much shorter half-life, and it decays by releasing a beta particle, and it becomes protactinium-234 with even a shorter half-life. So what we see is that one element that's radioactive decays into another, and that one that it decays into might be radioactive as well. So we go through this whole series, and as we're doing it, if you see what's happening, the nuclei are getting smaller and smaller and smaller. And then we get all different directions we can go. But at the bottom, I have lead-206. Now, the neutron to proton ratio for lead-206 is 1.51, for uranium 1.59. So you can see as uranium-238 goes through this decay series, the ratio gets smaller, more towards 1.5. And lead-206 then is stable, and that's where it stops. Okay. One thing you want to notice here with, we have radon in the middle here. You know, radon is a gas, a radioactive gas, whereas everything else here that I can see would be solids. Now, if this is happening in the ground someplace, there's no problem. But because this is a gas, it can migrate out, right into your cellar. And people have theorized that maybe radon gas entering somebody's home can cause lung cancers, because you notice that radon releases an alpha particle, and you would breathe in the gas, which is odorless and colorless, so you wouldn't know you're breathing it in. And then once it's in you and releasing alpha particles, it could cause damage. There's no definitive proof that this would happen, but people believe it can. Now, when you sell a home, you may have to have your home tested for radon gas. And they just leave a couple of vials in your cellar for a few days, and then they send it off to test for it. And you'd be surprised how many times they find radon gas in people's homes. But you notice, look at the half-life of it. Very short. So it doesn't last very long in a home. And many times, just by opening up windows, you can vent out this gas. And then again, it's in the cellar. How much is the air in the cellar mixing with the air in the home? Again, it depends on whether you have a finished cellar, maybe. So it's something to think about. Okay, radiation measurement is the next step. You can see here a fellow with a Geiger counter. A Geiger counter was actually created by two fellows, Geiger and Mueller. It used to be called the Geiger-Mueller counter. And it counts beta particles and alpha particles. So what happens is that the beta particles and the alpha particles can enter into the tube here, and they cause an electric current to be produced. So one electron is produced for each particle that enters. Now, alpha particles don't travel very far, so it really shows more for beta particles, because they can travel greater distances. You can actually count the particles being produced by that Geiger counter. And sometimes you see maybe a light going off. Now, if you have an awful lot of these particles and it's too hard to count them, you can say count every 10th or so, or every 100th if you have that many. Here are some units of radiation measurement. For activity, we have the Curie and the becquerel. You notice that the Curie measures the activity as the number of atoms that decay in 1 second. So we have 3.7 times 10 to the 10th disintegrations per second, or atoms decaying per second. It might seem like an awful lot, but you have an awful lot of atoms decaying, there really isn't that many. And so Curie was actually based on radium. It was radium atoms decaying. Now then we have the absorbed dose, or a rad, radiation that measures the radiation absorbed by the tissues of the body, so it's radiation absorbed dose. And then we have a REM, which is going to measure the biological damage of the radiation. This is probably the most important for us. And a REM is calculated by taking the number of rads that you're absorbing and multiplying it by a factor that's based on what type of radiation are you absorbing. Because as we see, different types of radiation can cause different amounts of damage. Some are much worse than others. Now, for the factors, we have beta and and gamma rays, beta particles and gamma rays, just you get a factor of 1, versus protons and neutrons with a factor of 10. So if you're exposed to the same number of neutrons as beta particles, the neutrons will cause 10 times the damage. And notice for the alpha particles, it's a factor of 20. Now we're talking internal damage. So if you were to ingest a substance that was emitting alpha particles, you're in a world of hurt. Right, this is a nice table here to check out. The average annual radiation received by a person in the United States in millirems, you notice. So natural background radiation in the ground, we have 20 millirems, air, water, food, 30, cosmic rays from the sun, 40, wood, concrete, brick, 50. They're again, small amounts of radioactive materials are just about everywhere. Then you have medical effects now. You have x-rays, dental and chest x-rays, a hip x-ray, a spinal x-ray, mammogram, 40, upper gastrointestinal x-ray, like a GI series, 200. So many times they have to give you a radioactive element in order to see to have that go into a particular organ. And then they can view the organ because they're really viewing the energy that's being produced by the radioactive element. And maybe your body puts those elements in only particular places. Then we go down here to television and air travel. Air travel because you're up closer to the sun when you're traveling by air. And then radon gas. So notice how it says varies widely. Yeah, and it really does. So and I mentioned radon earlier. If you're interested about effects of radon gas, you can have your house checked, and you might be surprised. And it's hard to predict it. You might think, oh, you have to have an awful lot of granite or something like that, but not necessarily. Next table: lethal doses of radiation for some life forms. Lethal dosage to kill 50% of the population, LD50. In REMS, look at how much it takes to get rid of the insects. Why would it take so much to kill insects? They're so much smaller than us. Well, for most of the insects, they're probably hidden. Most of them are in the ground, and that the earth would help to protect them somewhat. Bacterium, again, they're all over the place, but within the ground, and also they can reproduce so quickly, they'll last a long time. Humans, 500. Rats even more than us. So if there were a nuclear war, us and our dogs, we're going to go definitely. Probably most of the rats. Insects will go and inherit the earth. Wow. Something to think about.